Hello and welcome to this new lecture on compressible flow. In this lecture, we'll solve our first example, and I've included this example for you as a PDF file under the exercise files folder. So please go ahead and download this example and try to solve it by yourself. So I advise you to pause this video for a moment and solve the example by yourself. Here we have air that flows adiabatically through a duct. At point 1, the velocity is 240 meters per second with T1 equal to 320 Kelvin and P1 is 170 kilopascal. Compute in part A the stagnation temperature T0. So we need to find the stagnation temperature T0. As we said before, that for an adiabatic flow and in the absence of heat transfer, the stagnation enthalpy H0 will remain constant and it will be equal to H1 plus V1 square over 2. And we know that for an ideal gas, the enthalpy is related to the temperature by Cp(T), the specific heat at constant pressure Cp multiplied by the temperature T. So H0 now will be equal to Cpt0 equal to H1, which is Cpt1 plus V1 square over 2. So T0 will be T1 plus V1 square over 2Cp. Now to find T0, we know the temperature T1 and we know the velocity of air at point 1, V1. However, we don't know the specific heat Cp. Given in the problem, you can see that for air, K is 1.4 and the gas constant is 287. However, we can find the specific heat, Cp, from this equation, where Cp is Rk over K minus 1. So R, the gas constant, times the specific heat capacity ratio, 1.4 over 0.4, which is 1005 joule per kilogram Kelvin. Now let's replace everything in this equation to obtain T0. So we'll have T0 is T1 320 plus 240 square over 2 times 1005, which will be equal to 348.66 Kelvin. Now in part B, we need to find P0, the stagnation pressure, P0. To find the stagnation pressure, first I will draw a TS diagram, a temperature entropy diagram, a TS diagram. So let's identify on this TS diagram the stagnation temperature T0. So as we said, the stagnation temperature will remain a constant for an adiabatic flow. So this is T0. And it will be like this horizontal line for this problem, which is equal to 348.66. And at point 1, the fluid or the air will have a temperature equal to 320 Kelvin and a pressure P1, which is 170 kilopascal. So this is state 1. As we said that for the definition of the stagnation pressure, it is in fact the isentropic stagnation pressure. So to determine or to identify where is the stagnation pressure on this TS diagram, we can imagine an isentropic process from state 1, so this vertical line where the entropy will remain constant till we reach the stagnation temperature T0. So at the intersection here, we will have P0 and we will call it P01, simply because since we have an adiabatic process from point 1 to point 2, so if you continue reading the problem, you will have at point 2 further downstream, V2 is 290 meters per second and P2 is 135 kilopascal. So the velocity of air will increase from 240 to 290 meters per second, and also the pressure will decrease. So for this adiabatic process, we know that the entropy of air will increase for an adiabatic process. So here we have this adiabatic process from state 1 to state 2, where we have a temperature T2 and the pressure P2 is 135 kilopascal. And I'm drawing this process till we reach a lower temperature T2, because we know we said before as the air will increase in velocity, the velocity of air will increase. What will happen to the temperature? The temperature of air will decrease. Okay, so that's why I'm drawing another point 2, which is below point 1. Now, if we want to identify the stagnation pressure corresponding to state 2, also we need to imagine another isentropic process back to the stagnation condition. So at the intersection here, you will have P02. And you can see from this TS diagram that P01 will be greater than P02. So that's why to differentiate between the stagnation pressure P01 and P02, we will introduce the index here, because the stagnation pressure in this process will not remain constant. It will change, since this is an adiabatic process and not an isentropic process. Of course, for this adiabatic process, the stagnation temperature will remain constant. However, as you can see from the TS diagram, the stagnation pressure will change as we go from state 1 to state 2. Okay? Now, to calculate P0, and actually we will name it P01, since we have an isentropic process between state 1 and state not 1, so this is an isentropic process, we can apply the isentropic relationship between the pressure and the temperature. So you will say that P01 over P1 will be equal to T0. I will not write T01 or T02 because simply the stagnation temperature is the same across this process. The stagnation temperature for an adiabatic process will remain the same. So there is no difference between T01 and T02 since they are equal. So T0 over T1 to power K over K minus 1. And as we said, this equation is only valid for isentropic flow, and in fact here we're applying this equation between the state 1 and the state not 1, where the process is an isentropic process. Okay, of course you cannot apply this equation for example between state 1 and state 2, because from 1 to 2 we have an adiabatic process, however not an isentropic process, so a non-isentropic process if we want to say. So let's find P01 is P1 170 into T0 348.66 over T1 320 to power 1.4 over 0.4. So this will be equal to 229.53 kilopascal. So this is one way of finding the stagnation pressure P01. In fact, there is another way by using the compressible flow tables. So if you go ahead and open the compressible flow tables.pdf, to find the P01, in fact, since we know the temperature T1 and we know T0, we can calculate the ratio T1 over T0. So for this ratio, you can search in column number 4 for the value of T1 over T0, and you can in fact read the corresponding P over P0 ratio. So when you read the corresponding P1 over P0, since you know P1, you can find P01. Okay, so let's see how to do this. So first, we need to find T1 over T0, 320 over 348.66, which is equal to 0.9178. So let's search for this value. If we scroll down, we will have 0.9199 and 0.9153. So in fact, our value here is in between these two values. So we need to do a linear interpolation since we don't have this exact value in the table. So to do this linear interpolation, you select these two rows And we need to do a linear interpolation between the ratio of temperature T over T naught, so in column number 4, and the ratio of pressure in column number 2. So in column number 4 we have 0.9199. This corresponds to a pressure ratio of 0.7465. And also at a temperature ratio of 0.9153, we have a pressure ratio of 0.7338. So our exact temperature ratio T1 over T naught, which is 0.9178, we need to find the pressure ratio P1 over P01. So to do this linear interpolation, I will teach you a very fast way to do this. Simply you subtract the second row and the first row, and you divide by the subtraction between the third and the first. So the second, 0.9178, minus the first, 0.9199, divided by the third row, 0.9153, minus the first, 0.9199. And this will be equal also on the pressure, the same, the second minus the first, divided by the third minus the first. 0.7465 divided by 0.7338 minus 0.7465. So you calculate now P1 over P01, which will be equal to 0.7407. So now since we know the pressure P1, we can find P01. So P01 will be equal to P1, 170 kilopascal, divided by 0.7407, which will be equal to 229.51 kilopascal. So this is very close to the pressure that we have obtained using the isentropic relationship. So you can use any way, any method that you like. Simply here I'm showing you every way you can use to find the stagnation pressure P01. So you may be comfortable using the equation, or also you may prefer to use the table. So these are the two ways to find the stagnation pressure. Now in part C, we need to find the stagnation density ρ naught. And also this corresponds to ρ naught 1, because the stagnation density at naught 1 will be different from the stagnation density at naught 2. Okay, because simply the pressure will change. So the easiest way to find the stagnation density is to apply the ideal gas law. We said that P naught, we can say P naught 1 is equal to ρ naught 1 R T naught. So T naught, as we said, we will not write T naught 1 or T naught 2 simply because they are the same. The stagnation temperature will remain the same for an adiabatic flow. So ρ naught 1 is P naught 1, which is 229.51 times 10 to power 3 over 287 times T naught, which is 348.66. So this will be equal to 2.29 kilograms per meter cube. Now in part D, we need to find the Mach number in part D, the Mach number. So the Mach number at state 1 or at point 1 is the ratio of the velocity v1 to the speed of sound c1. So v1 over the speed of sound at point 1 is the square root of kr t1. So please pay attention here that the speed of sound will not remain constant for this flow, because as we said that the speed of sound is proportional to the square root of the temperature. And since the temperature is changing for this air, as the air goes from point 1 to point 2, the temperature will change from T1 to T2. So as a result, also the speed of sound will change. So when you calculate the Mach number at at a given point, you need to divide by the speed of sound at the temperature, evaluated at the temperature at this point. Okay. So here we have V1, which is 240 divided by the square root of 1.4 into 287 times T1. So T1 is 320 Kelvin. So this will be equal to 0.67. Also, we can find the Mach number using the table, of course, because we have already found T1 over T0, the ratio of the temperature, T1 over T0, which is 0.9178. And if we open the compressible flow tables.pdf, in the first column we have the values for the Mach number. So you can simply interpolate between the temperature ratio, which is in column number 4, and the Mach number, which is in column number 1. So you can say at a temperature ratio of 0.9199, we have a Mach number of 0.66. And at 0.9153, we have a Mach number of 0.68. So at T1 over T0, which is 0.9178, what will be the Mach number 1? Or Mach 1? So we do the linear interpolation similarly as before. So 0. The second row minus the first divided by the third minus the first. So 0.9178 minus 0.9199 divided by 0.9153 minus 0.9199 will be equal to Mach number 1 minus 0.66 over 0.68 minus 0.66. And of course, if you do the calculation, you will obtain a Mach number equal similarly to this value here, which is 0.67. Okay. Now, in part E, we need to find V star, the critical velocity. And we said, whenever you see this star, it means that we need to evaluate the property at the sonic condition when the Mach number is equal to 1. So when the Mach number is equal to 1, V star will be equal to the speed of sound C. And here the speed of sound C should be evaluated at the critical condition. So we will say it will be equal to C star, because as we said, the speed of sound will vary with respect to the temperature. So at the sonic condition, the temperature will be the critical temperature. So the speed of sound will be equal to the square root of KR T star. So to find this V star, we need to find first T star. And we said that at a critical condition, the ratio of T star over T naught will be equal to 0.8333. And this is valid when K is equal to 1.4, which is the case here. And if you go also to the table and you scroll to Mach number equal to 1, so let's say we go to the right here, at Mach number equal to 1, you can see here the critical ratios. P star over P naught 0.5283, rho star over rho naught, and T star over T naught, which is 0.8333. And this is valid for K equal to 1.4, because you can see here in the title we have table B1, isentropic flow of a perfect gas when K is equal to 1.4. So actually you should also be careful that this table is only valid when the specific heat capacity ratio is equal to 1.4, and of course is only valid for isentropic flow of ideal gas. Now let's go back to the problem and find T star. So T star will be equal to 0.8333 times T naught, which is 348.66, which will be equal to 290.54 Kelvin. So now we can find V star. V star will be equal to the square root of 1.4 into 287 into T star, which is 290.54, which will be equal to 341.67 meters per second. Now let's continue the problem. At point 2, further downstream, the velocity will increase to 290 meters per second and the pressure will decrease to 135 kilopascal. What is the stagnation pressure P02? So to find the stagnation pressure P02, as we said, we can imagine an isentropic process between state 2 and state not 2. And for this isentropic process, we can apply the isentropic relationship. So we said that P02 over P2 is equal to T0 over T2 to power K over K minus 1. So at this point, we know the pressure P2 and the temperature T0, the stagnation temperature will remain the same. T2, however, here is not given. And what is given is P2, which is 135, and given is the velocity V2, in fact. So we cannot find P02 without finding the temperature first. So to find the temperature first, we need to say that for adiabatic flow, as we said, for an adiabatic flow, the stagnation enthalpy will remain the same. So H01 will be equal to H02. And in fact, this will lead to saying that the stagnation temperature also will remain the same. So CPT01 will be equal also to CPT02, and for the same CP, the temperature will remain the same. So H01 is H1 plus V1 square over 2, and H02 is H2 plus V2 square over 2. So, and since we know that H is CPT, we can say CPT1 plus V1 square over 2 is equal to CPT2 plus V2 square over 2. So let's find T2 now. T2 will be T1 plus V1 square minus V2 square over 2CP. So T1 is 320 Kelvin plus V1 square, which is 240 square minus 290 square over 2CP, which will be equal to 306.82 Kelvin. So now we know T2, we can apply this equation here to find the stagnation pressure P02. So P02 will be equal to P2 into T0 divided by T2 to power K over K minus 1. So P02 will be equal to 211.18 kilopascal. And as predicted, you can see that the stagnation pressure at state 2 is smaller than the stagnation at pressure at state 1, which is P01 229.51. Okay, so another way to find this stagnation pressure, in fact, is to use the table. Now we have calculated T2, you can find the ratio T2 over T0, 306.82 over T0, 348.66, which will be equal to approximately 0.88. So let's find this ratio in the table. So let's search in column number 4 for 0.88. If we go up here, 0.88. So we have 0.8815 and 0.8763. So between these two rows here. And let's do a linear interpolation. So at 0.8815, we have a pressure ratio of 0.643, and at a temperature ratio of 0.8763, we have a pressure ratio of 0.63. So at T2 over T0, which is 0.88, what will be the pressure ratio? P2 over P02. So also, you can do a linear interpolation. The second row minus the first, as we said, over the third minus the first, which will be equal to the second row minus the first over the third minus the first. So we can find P2 over P02 in this case will be equal to 0.6393. So P02 will be equal to P2 over 0.6393. So this will be also 211.18 kilopascal. So the same value obtained using the isentropic relationship. So now this is the end of this example, and I hope that you were able to solve this problem. If not, don't worry, we will solve many problems in this course. So let's practice more in the next video and try to solve another problem.